Today I'm going to introduce the first numerical method, the most common numerical method that you've likely seen in the past and that we will use every now and then before we touch on the finite volume method. So today's method is the finite difference method. And we will start by revisiting the sequence of steps that we discussed in the first lecture. So first we have to formulate a set of governing equations. When we're doing CFD, you have to know what you're solving. Now that we know kind of what we're solving, Navier Stokes equations plus or minus an energy equation, in one form or another, we haven't really settled on an algorithm yet. So we're going to discuss a numerical method first. So after we develop a mathematical model, governing equations, boundary conditions, etc., the next step is to convert all of the terms in the all the derivatives in the governing equation into values that a computer can understand. So those would be discrete values on a what we call a computational grid. This process is called discretization. Okay, we will learn about the finite difference method. We're going to refer to that as FDM, and the finite volume method we'll refer to that as FDM. The finite difference method is as old as our friendly scientist. Do you know who this guy is? Yes, Euler. You should know who this guy is. This guy is everywhere. He has his name on every theorem. If you think you are a genius and you thought of something, check with Euler first, because he very likely he beat you to it. Amazing person. So anyway, the goal of the finite difference method is to approximate derivatives, and that's kind of where differential calculus or finite difference calculus started. And the most basic definition of a derivative that you are familiar with is likely this formula. Essentially taking the limit of, if you have a function and you go, let's say you're walking on a function, if you move 1 unit in the x direction, so that's your run, how much are you rising? So the definition of the derivative is rise over run, and in the limit as the run goes to 0, that gives you the formal definition of a derivative. But discretely, this is kind of one of the earliest definitions of a derivative. But what do we mean by that? Essentially, this kind of discrete form is that if you have a set of known values, we are trying to find the derivative of the function u, or the rate of change of the function u at a point xi, or the slope of the function u at a point xi. So the idea is, if you have values for the function u at different points xi, you can find the derivative at any point by using 2 other neighboring points. So let me give you just a quick example that I came up with. So let's say you have a set of data, x values 0, 0.1, 0.3, 0.5, and a bunch of values for the f function or u function, and those are plotted over here. You will notice that the spacing between the different points is not equal. The spacing here is 0.1, the spacing here is 0.2, the spacing here is 0.2, but this function is plotted over here. And let's say you want to find the derivative at this point, or the slope of the function at that point. Okay, what do? You can just use that formula and say df by dx at this point, given the data that we have. We only have these discrete data. We cannot invent new data here. Just simply say the derivative here is the function value at that point minus the function value at this point over the distance. Okay, so that's the rise, f of x plus delta x minus f of x. So that's this guy over that guy. Okay, and of course, as you have more data, your derivative is going to be more and more accurate. So in practice, in this case, we have a set of data, given at points x1, x2, all the way endpoints. So let's say you go run an experiment, you collect data at x values. These are your independent variable, and you collect also function values at each one of those points. And we're going to lay them out like this on what we're going to call a grid. Okay, so we call these grid points. The spacing between the two different between any 2 different points doesn't have to be equal to any other set of points. So you may be, let's say, measuring a reaction rate, and sometimes you miss with your timer. You can measure at 1 second, then at 2-second intervals, then at 0.5-second intervals. The spacing doesn't have to be equal. But for our purposes and for simplicity, we're going to assume that the spacing between these points is equal. okay? And it really doesn't make a big difference, just simplifies the implementation, okay? And this is what we care about, because we want to learn more, we want to gain insight into these problems, not get involved in the minutia of unequal spacing and whatnot, okay? So then, experimentally, this is kind of what you have. You have a set of data points given by independent variable and function values, and you typically want to find the rate of change of the function u as you go through the independent variable. And so our derivative right now note one thing. As I index the values on the grid, and you're all kind of familiar with this, right? We're calling points x1, x2, xi, etc. The function value at point x1, we're going to call it u1, function value at point x2, u2, function value at point I, ui, rather than saying u of xi, okay, just to simplify things a little bit, okay? So then the derivative, by the definition that we saw earlier, is given by the derivative at point I, so essentially du dx at point xi, is u at xi plus 1, or ui plus 1, minus ui over delta x. So then you can kind of simplify the notation quite a bit in your mind, okay? Now, this approximation uses points I plus 1 and point I to get the derivative at point I, okay? We call this a stencil. So essentially, what's a stencil? It's the set of points that are involved in your approximation, okay? So in this case, our stencil is points I plus 1 and point I, okay? So it turns out there is a more generic nomenclature for a stencil. So don't look at this definition first. Let me give you a bunch of examples. So let's say you approximate the derivative by using points I and I plus 1. How do you define the stencil here? You put two numbers in a bracket, two integers in a bracket, 0 and 1. This is essentially saying this is going to use point I. Okay, so this is the stencil for evaluating a derivative, any derivative, second, third, whatever, at point I. 0 says this is the point at which I'm evaluating the derivative, so that would be point I. 1, this is I plus 1. Okay, so 0 and 1 imply points I and I plus 1. So therefore, your derivative is going to look like some coefficient times ui plus some other coefficient times ui plus 1. Okay, so going back to this derivative, what is the stencil here? It's 0, 1. What is the coefficient for ui? Minus 1 over delta x. Coefficient for ui plus 1 is 1 over delta x. Okay? So these are these coefficients. What about this stencil, minus 1, 0, 1? Okay, so don't look here. This is saying at point I, we're going to use point I minus 1, and point I plus 1. Okay? So then the formula for the derivative is going to look like a coefficient times ui minus 1. We're going to call that alpha minus 1 plus alpha 0 ui plus alpha 1 ui plus 1. And these alphas will have 1 over delta x, etc. In one of your homeworks, you'll see how you can derive these alphas. So how do we go about finding these approximations? So this is great so far. We know that this derivative, we kind of learned that in high school. But how can we formally obtain different stencils? What if you are at the boundary over there at un, at point un, and you don't have any points un plus 1? How do you evaluate the derivative here? So you want point n minus 1. Can you get a derivative using points, previous points, minus 1? Yes, of course. So how do we go about getting those? We'll describe one method based on the Taylor series. Okay? To obtain other types of approximation, we're going to use the Taylor series. Now recall that the Taylor series of a function f of x in the neighborhood of a point x0 is given by this infinite series. It says that, so the way to think about the Taylor series intuitively is, if you know everything about a function at any point x0, so you know the function value, you know its derivative, first derivative, second derivative, all derivatives, then using all those information, all those data, you can combine them and predict the function value in the neighborhood of x0. Okay? So this is saying the function value at point x that I don't know. I don't know what the function value is at point x. but I'm assuming that I know the function value at point x0 and the derivative and the second derivative and so on, then the Taylor series is this infinite series saying f of x is f at x0 plus the distance between x and x0. So think of this in the neighborhood of x0. You know everything here. This is x0. You know f, f prime, f double prime, etc. In the neighborhood of x0, okay, x, and this would be delta x, which is x minus x0. In the neighborhood, can you evaluate the function? Yes, we can evaluate the function using this Taylor series. So f of x naught plus f prime times the distance between the new point and the point you know, etc., all the way to infinity. Okay, this is great. All right, now we're going to take this and apply it to the grid. Okay, so now we're going to change the nomenclature a little bit and say we want to write the Taylor series for a function f at point xi plus 1, okay, in the neighborhood of point xi. So I'm assuming that I know the function, everything about the function at point xi. So let's get the Taylor series at point I plus 1. And instead of using f, I'm going to use u. Okay? So u xi plus 1, correct? Compare that to this guy, is u at xi. So I'm assuming I know the value at xi, plus xi plus 1 minus xi times u prime xi, and so on. Can you agree that these are the same? Okay. Now let's simplify nomenclature a little bit. U at xi plus 1, it's ui plus 1, and u at xi is ui, etc. Xi plus 1 minus xi, we're going to assume equal spacing, like we said. So that's going to be a delta x. So then, pardon me, your Taylor series at point I plus 1 around in the neighborhood of point I looks like this. ui plus 1 is ui plus delta x u prime I plus 1 over 2 delta x squared u double prime, etc., etc. Okay, this is great. Now, remember, what are we after? Okay, so two things we have. So we started off with the Taylor series by assuming that we actually know everything about the function at point I. Now I'm going to say, okay, forget about that. We don't know anything. We only know the ui values. We don't know any of the derivatives. We don't know u prime I. We don't know u double prime. We don't know any of those. We only know ui plus 1, ui minus 1, etc. Okay? So we're going to invert that logic a little bit now. And remember, we are after u prime I. So then I'm going to make the bold claim of solving for u prime I. So this is still all exact mathematics now. Okay? This is still exact. There's a perfect equal sign here. Okay? So now we're going to solve for u prime I. Gonna, if you want, take it to the left and move this guy over here, and then do the sign balance, etc. Then you get u prime I is ui plus 1 minus ui over delta x minus a bunch of other terms. Okay? Now you start seeing this is looking very, very similar to our definition of the derivative. Okay? So now we take that, and okay, we look at this. We are after u prime I. We know ui plus 1. We know ui. Those were measured experimentally, correct? We do not know u double prime I. Okay, we don't know u triple prime I, etc. So let's make the bold claim and say, hey, you know, we're going to neglect all of these terms. How can we do that? Well, you could say, if I refine my measurements, if I take more measurements, as delta x shrinks, these terms are going to start disappearing. On the condition, this is a footnote, that u double prime and triple prime are bounded. You know, they're not infinite. Okay? So assuming that, all of these terms actually will be way, way smaller than this term. Because as you drive delta x smaller, this guy shrinks and this guy goes up, right? And so in the limit, actually these terms, they do disappear. And then we make the approximation. So now we switch from exact. This is still exact math. This is inexact now. This is approximate. Then we're going to say, okay, u prime I is approximately equal to ui plus 1 minus ui. But obviously, we committed an error, right? So this is the exact u prime I. This is the approximate. Then what is the error between the two? Yeah, it's the difference. So essentially, the error is u prime I exact, this guy, minus u prime I approximate. And that essentially is all of these all of these terms. We call that the truncation error. Why? Because we truncated. We said, forget about all of these. Okay, we truncated. That's the truncation error. Okay, so that error actually exists and will show up in our numerical simulations, and we'll have plenty of opportunity to understand what it implies. But for now, let's just follow this analysis. And it turns out that in truncation error analysis, you can show that as long as u double primes are, the derivatives are bounded, this term, the leading order term, or the first term in the truncation error, dominates the error. Okay, so really, if you want to evaluate, so let's say you have 5 investors hanging out in a bar. One investor is Bill Gates, and then you have your average Joe. That Bill Gates has a few $1 billion, and your average Joe maybe has $100,000. Would it be safe to say, well, the average investor in this bar has the value of Bill Gates because, right, $10 billion versus $10 billion plus a few $100,000 is not going to make a difference. So essentially, the leading order term is Bill Gates, or is this guy, the leading order term here, that dominates the error. Okay? So then we can show that all of these terms are dominated by this guy, C delta x. So essentially, it's a constant. The error can be approximated by a constant times delta x, the leading order error. Okay, so if you had delta x squared here, this would be C delta x squared. And then we call that this truncation error, for this particular case, is order delta x. Okay, so what does that mean? An approximation is of order delta x means that if you cut delta x in half, then the error in your approximation is going to be cut in half. Make sense? In other words, if you double the number of grid points, you're going to reduce the error by half. Okay? Okay. So now in general, we write this. If you want to use exact mathematics, you just say u prime I is approximation plus an error of order delta x. This capital O essentially is telling us that the error is bounded and behaves as C delta x. Okay? Now, in general, an approximation is said to be of order p, or order delta x to the p, or the order of accuracy of a method is p, if the error is proportional to delta x to the p. Okay, so let me give you an example. A second order method has an error of delta x squared. Okay? So what happens if you double the number of grid points? So delta x is cut in half. Then your error is going to be cut by a fourth, right? What if you have a third order error? What does that mean? That's order delta x to the 3, or delta x cubed. Then if you cut delta x in half, or you double your number of grid points, I want you to think of it intuitively like that. What happens to your error? You're going to cut your error by an eighth. You can imagine the implications of that. So in practice, let me show you some math to back up my claims. We said the truncation error, capital E, is C delta x to the p. That's a pth order method, okay? Now, I'm going to take the logarithm on both sides because I want to rip out that p, okay? And I want to show you how that looks like on a plot. So log of the error is p log delta x plus log c, right? Clear? Okay. Now I'm just going to do one more thing. I'm going to take the inverse of delta x, so that gives me a negative sign. Okay, so log e is minus p log 1 over delta x plus log c. What does this look like? It looks like the equation of a straight line, right? Where y is log e is minus p x log 1 over x plus b. So on a log-log plot, if you plot the log of the error versus the log of 1 over delta x, then you're going to see straight lines whose slope is your order of accuracy. So this is going to be instrumental when we analyze the order of accuracy of an implementation. So we compute the error. Somehow we learn how to compute the error. And then we refine our number of grid points and compute another error. And then refine, compute another error, and create a plot. And a log-log plot, log of the error, log 1 over delta x. And the slope of the lines on that plot are going to tell you what the order of accuracy of your method is. Okay? So for example, this goes back to the example. This is a log-log plot of the error versus 1 over delta x. So going in this direction means we are decreasing delta x, or we are putting more grid points. So it makes sense for the error to get smaller, right? For a first order method, you see a line with a slope of 1. For a second order, the line has a slope of 2. Third order, line has a slope of 3. Minus 3, minus 2, minus 1, okay? Minus, plus, whatever. But this is a third order method, second order, first order method, okay? Now this has serious implications in practice. Let's say you have a grid, you're solving a problem, okay? Let's say you start with 11 grid points. So that's 10 intervals. Your delta x is 0.1. If you're using a first order method, your error is of the order, remember, delta x. Order is proportional to delta x. So your error is on the order of 10% for a first order method. But for a second order method, your error is on the order of 1%. Now, what would it take to make a first order method make an error of 1%? You have to double the number of grid points. So you have to use 100, so 1 order of magnitude more in this case. Okay, you have to use, no, sorry, I made a mistake here. No, yes. So yes, you have to get to an error of 1%. Okay, you had to get 100 grid points. Okay, so that's an order of magnitude more higher than your initial guess. Now imagine, in terms of, go in 3D and imagine you're doing this in time. This is very costly. Whereas you can accomplish the same error if you use a second order method. Now, you would say that, oh yeah, we should use a 10th order method. Well, higher order methods have their own ailments as well. We will see that higher order methods can lead for advection terms. They can lead to instabilities and a ton of other things, okay? So then first order methods are a little bit more attractive because they can be diffusive, et cetera. These are properties that we will all learn about. Okay, so now we saw kind of the formalism with the Taylor series and what the implication of the error is. But let's go back to the problem of getting a different stencils. So far we were stuck with the 0, 1 stencil, right? I plus 1 and I. What if you want I minus 1 and I, or I minus 1 and I plus 1 and I? Okay, so we can obtain all sorts of stencils for derivatives by combining Taylor series. You just have to be intelligent and kind of smart about where you write your Taylor series. So we wrote the Taylor series at point I plus 1 around point I. You can write it at point I minus 1 around point I, or I minus 2, or I plus 2. And if you combine the Taylor series in certain ways, you can get all sorts of stencil combinations, okay? So for example, the backward difference formula, rather than using I plus 1 and I, what if you want to use I minus 1 and I? So that's if you're doing discretization at the right at the boundary to the right, then you write the Taylor series at point I minus 1, and then you get your first derivative from this formula, and then you get the backward difference formula, okay? Now, what happens when you combine ui minus 1 and ui plus 1? If you combine them together, you get another definition for the derivative, but look what happens now. This is called the central difference formula. It gives you the derivative at point I using I plus 1 and I minus 1, but it has a second order error, okay? So whenever you can, if you can get a second order error, go for that, okay? So in evaluating derivatives on that line, you should probably use this one. So we can obtain all sorts of different stencils and different orders of accuracy. Let's say you want a one-sided formula, so either forward or backward, that is second order. So if we go back to the grid points I showed you earlier, let's say you use a central difference formula everywhere on the interior, because you need I plus 1 and I minus 1. Obviously, you cannot use it at the boundaries, because you don't have any more points, outside the domain. So you use a second order everywhere. What happens at the boundaries? if you use a first order method, that is going to kill your global accuracy, right? Because at the boundaries you used a first order method, and on the interior you used a second order method. So what should you do in that case? At the boundaries, you should use second order one-sided methods. Okay, so essentially you use a forward difference on the left boundary that's second order, and a backward difference that's second order on the right boundary. I will give you the discretization type, if I ask you for something, and I have a table here discussing kind of all of these guys. So a forward difference order delta x and a backward difference order delta x, we saw that. Okay, fi plus 1 minus fi or delta x, fi minus 1 delta x. Central difference, second order, fi plus 1, fi minus 1. Forget about these two guys. We will discuss those later. And then what if you wanted a second order forward difference? So on the left boundary at point 1, how do you get a second order difference using only interior points? As this says this is fi plus 4 fi plus 1 minus fi plus 2. So you're using only points from the interior, and that gives you an error of delta x squared. Okay? On the right boundary, or the boundary to the right, you want to use points I minus 1 and I minus 2, second order to be consistent. So if you're using central difference in the middle, you use second order forward, second order backward on the left and right. And we can do the same thing with second derivatives, essentially combining different Taylor series around I plus 1, I minus 1, I, etc. You can verify that for yourself. What you essentially do, you take fi, you write the Taylor series for fi plus 1, Taylor series for fi plus 2, you plug them in, and you can verify that this is actually order delta x squared, etc. Okay? This is going to be the most important one that we will be using because it's a central difference, second order. Okay, so this is great. This applies to known data. Okay, so you're given data. You know the values of the function u at the different points x. You know the values of the dependent variable as a function of the independent variable. Okay, but in reality, so take the Navier Stokes equations. You have derivatives in there, okay? And we know how to approximate derivatives, but we don't know the function values. We are, in fact, after we are looking for the function values at those discrete points. So how can we apply this concept of discrete derivatives to differential equations? Pretty simple. Essentially, you just take these approximations that we just derived and just plug them in and see what happens. And you'll end up with a system of equations maybe to solve for those unknowns. So here's a systematic way of thinking about this. The first step you want to do, now that you formulated the problem, you know your governing equations, you know your boundary conditions, you know your domain size, you know everything about the problem, and you kind of know what finite difference method you want to apply. First thing you want to do is chop your computational domain into discrete points. So we're trying to mimic the experiment. Okay, we are trying to mimic the discrete values measured by experiment. Okay, so you chop your computational domain in 1D. We're just going to say n points. Okay, so those go from 1 to n. Delta x is defined, be very careful in this definition. Delta x is the length of the domain over n minus 1. So you have n points, but n minus 1 intervals. So for 11 points, you have 10 intervals. Okay, for 101 points, you have 100 intervals. So that's why I was using those weird numbers earlier within the table, 11 points and 101 points. Okay. In 2D, same thing. You specify a number of grid points in the x direction and a number of grid points in the y direction. Okay. Now, notice one thing about the finite difference method is that your grid points at the boundary, they coincide with the boundary. So if you had a wall over here, these points are on the wall. And if you know what the conditions on the wall are, you kind of know the discrete values at those points. So you're given some information in the finite difference case. Okay? We will see that the finite volume method is different. The finite volume method does not locate the grid points at the boundaries, kind of locates them in the middle. Okay. But note the indexing here. We're going to start from, we have two indices here, in the x direction and the y direction. We're going to call the indexing in the x direction I, and in the y direction j. Okay? So each point is assigned two indices, starting with 1, 1. So that's I equal 1, j equal 1. That's the first point in the domain. 2, 1 is the second point in the x direction, still first point in the y direction. 1, 2 is the opposite, first point in the x direction and second point in the y direction. An arbitrary point is given by the indices, by the tuple ij. Okay? Same thing in 3D. You have ijk. Okay? Clear so far? Same thing for delta x, delta y. Delta x is the length in x divided by nx minus 1. So you have 1, 2, 3, 4, 5 points here. You have 4 intervals, 1, 2, 3, 4. If you forget, just draw a grid and put points and count the intervals, count the number of points. Missing this could mess up your code big time. We've seen this before in my group. Okay. Now, the next step is to assign a value for the solution variable we're looking for. Many of you have done this, know this, so please bear with me. I'm just kind of trying to be as thorough as possible and as fast as possible. Okay, so let's say we're solving for our canonical variable u. Okay, we're gonna assign a value at each point, at each grid point. We're gonna assign a value for u. So at point 1, u1, u2, at point I, ui, at point n, un. Okay, so now you start thinking numerically. This is an array. This is a list of points of unknowns. Okay, so at this stage we don't know what these values are. Okay. We may know the values at the boundary, but in general, we don't know what these values are. Same thing in 2D, except that in 2D you have now a two-dimensional array. Okay, u, I, j. All right. So we just assigned a value at each one of those points. Okay. Now this is the most important step. Since the governing equations are so our governing equations, the Navier Stokes or any advection diffusion equation. Can I see on this? Okay, they're tell me if it's if it's shaking. So they are valid. The equations are valid on the entire domain. Okay, at every point in the domain. So they should be valid at the discrete points that we have chosen. Correct? So if you think of your computational domain as, so this is computational domain, the governing equations, they're valid everywhere. Here, 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 there, here. And also at these guys, right? We just chose a set of points that is convenient for us, that logically makes sense. But the governing equations, they're valid everywhere. So rigorously and correctly, we can for sure apply our governing equation to each and every one of those grid points, right? So at point 1, I'm going to take my differential equation, which I'm going to write as d by dt equals some right-hand side. Okay, du by dt at point 1 is equal to some right-hand side of u. So this could have convection, diffusion as source term, or could have only convection or only diffusion. Okay? So think of this as the Navier Stokes equation, right? So this would be du by dt equal u dot grad u plus minus del u plus del u del squared u, etc., right? Minus grad p. And same thing, dv by dt, okay, at each and every point. Now, there's a question mark here, and those are the same question mark, okay? They're the same question mark. So we've applied this time derivative and the right-hand side at point 1, but we haven't specified the time level yet. Now, bear with me for a few minutes until we get to the time integration, because so far we've covered finite difference we gave examples in the spatial sense, d by dx, right? We're going to do the same thing for d by dt, but turns out there's a fourth dimension for time, okay? But for now, don't worry about this. Just recognize that we can take the continuous differential equation and say, hey, this differential equation is valid at this grid point. Of course it is, right? Because it's valid everywhere. And same thing, you take your differential equation and apply it at point 2, and then you can take it and apply it at any point I in your domain. Okay? Is this clear so far? Okay, so this is step 3. Apply or recognize. I mean, it's kind of a moot point, like, yeah, of course, the differential equation is going to be valid at each one of those discrete points. And finally, and the last and most important step is, at each one of those points, convert the derivatives, the spatial and time derivatives, into their algebraic equivalent. So we saw how du by dx is ui plus 1 minus ui over delta x. That gives you a relation between point I plus 1 and point I. And if you go to point I plus 1 and apply the same relation, it's going to give you a relation between ui plus 2 and ui plus 1. And when you apply it everywhere, you're going to get a system of equations that you can solve for and then find what you're looking for. So you see how interesting this is? I mean, we started off without knowing anything about the solution. We blindly applied a finite difference approximation for all the derivatives. And then we solved for the unknowns, because it turns out when you apply the finite difference, you will end up with a system of equations. So let me give you an example. We'll start with an ODE, no time involved. So this is just one-dimensional in space. And we are trying to look for, so you have a rod, a rod that is being heated at both ends. So think of this as a, so I give this example in my undergraduate numerical methods class. Don't be offended, but it's a very important kind of example just to fixate those ideas in your mind. So I give the example of a spatula. I love to cook a lot, so I always burn my hands because I use, copper or metal spatulas, because has to be. I'm very strict about the spatulas I use, but they end up getting really hot, and I always forget to grab an oven mitt to hold them. And so, you have the spatula in this boiling water, or just this large spoon, metal spoon, that is, in this boiling water, and that's exposed to a different, to the atmosphere, and a different boundary condition on the other end. And so this is kind of the example. You have this rod, metal rod, that is immersed at two different temperatures on the left and on the right, and that's being exposed to air or the environment at T infinity. We call this is the ambient temperature. This is the infinite sink of the atmosphere that kind of cools everything down. Okay. Now, at steady state and under certain assumptions, I'm not going to go through the physics of this. This is the governing equation for the temperature distribution inside the rod. Pardon me. So let's say you are after the temperature value at each point inside the rod. The governing equation for the heat transfer between these 2 points being at different temperatures and the ambient air is given by this steady state heat equation for the temperature. Second derivative for the temperature is equal to the rate of heat transfer to the environment. That's H, heat transfer coefficient, P, perimeter of the rod, lambda, a diffusion coefficient, and the area, AC, cross-sectional area of the rod, times T minus T infinity. T is the same T. That's the point-wise temperature. Okay. T infinity is the ambient temperature. So HP, lambda, AC are given to you. So is T infinity. You are trying to find the solution for T. Okay. And you're also given the boundary conditions at the left and at the right. Okay. Is this clear so far? Okay. Think of this as just a number. And, we can solve this as assuming this is just a number and see what happens if you increase it or decrease it. Okay. So we can do with different data. Let's not worry about this. Okay. So the first step is we know our, so far we know our domain. We know our governing equation. Let's start applying, doing numerical methods. Okay. First step is to discretize the space domain. So we're going to chop it into n number of points. And so this is the first point. We know the value. So this is the nice thing about the finite difference method, is that the boundary conditions, they give you one of the values. Each boundary condition is going to give you a set of values for your discrete solution. Okay. So, and this is the governing equation. Step 2 is to assign a value for the temperature at each grid point. So T1 is T left, that's given to you. Tn is T right, that's given to you. And we're going to put a bunch of points in the middle. T2, T3, Ti, Tn minus 1, and Tn. Okay. Now we're going to apply this governing equation to each and every grid point. We know that it applies, but we're going to convert the derivatives into algebraic relations between neighboring points. So there are no derivatives on the right-hand side. This is the only derivative here. and I'm going to use a central difference approximation. If you go to the table before, at point I, the second derivative is given by this relation, this approximation. You see the approximate sign? So at point I, you are relating ti minus 1 and ti plus 1 and ti. So it tells you this is approximated by ti minus 1 minus 2ti plus ti plus 1 over delta x squared equal what? We said we're going to apply this governing equation to point I. So we just take the right-hand side and apply it at point I. Okay? So what are the unknowns here? Yeah, the ti's, ti minus 1, ti, and ti plus 1. Everything else is known. Okay? So we will do some algebraic manipulation to simplify the equation. On the left, I'm going to put all the unknowns, and on the right, I'm going to put everything that we know. So at an arbitrary point I, so this I could be t3, it could be t25, could be any point. Okay? At arbitrary point I, we have this formula now. This algebraic relation, ti minus 1 minus 2, etc., ti plus 1 equal this guy. Okay? So this looks like a linear equation, right? Okay. So, but notice that this only applies at interior points. So starting from t2 to tn minus 1, because you want. So if this is 2, this will be 1. You can't apply this formula at point 1 because there's no point outside the domain, and besides, you know the value at point 1. Anyway, so we'll discuss that in a second. So now we take this generic formula at point I, okay, and I'm going to show you what it looks like at each and every point. So at point 2, you simply put I equal 2, and you're going to get t1 minus something times t2 plus t3 equal minus etc. t infinity. Okay. At point 3, it's going to look the same, right? We're just using, we have different variables. Okay. Point 4, etc., all the way to point n minus 1. Okay. Now, there's just two more things here, t1 and tn. Essentially, we either plug the values in here directly or augment the system by an additional equation. Say t1 equal t left and tn equal t right. Whichever one you choose is okay. But what is this? This is a system of linear equations. What are the unknowns? They're t2, t3, t4, all the way to tn minus 1. It's pretty interesting, right? Who has not done this before? Okay, you've all done it. What class did you do it in? Okay. Okay, so you're pretty familiar, and you guys did it in. Okay. All right, so if this is boring, let me know. I can go even faster. Is it boring? No, not. Still help. Okay, good. It's always sometimes, I personally find it refreshing sometimes to revisit material I know, because it's always going to be presented in from a different perspective. And that different perspective is most likely going to fill a gap that you've had you've had a question, that's been nagging you or not certain of. So, okay, I hope I'm not boring you too much. And as I tell my students in numerical methods, we always write systems of equations in matrix form. So we collect all of the coefficients and put them in a matrix, and collect the unknowns, put them in a vector, and everything we know, we put it on the right-hand side. Okay? Do you want me to solve this in Python in front of you? So let's see how much time we have. Okay, so let's go through. Maybe we're going to have to do it. We're going to have to do something similar for the advection equation in a few minutes anyway. So let's assume you know how to do this in MATLAB. Okay, so essentially you just take this matrix, you put it in, set the numbers, solve the system of equations, and you get the steady state distribution for the temperature. Okay? Can we do this in 2D? Of course, absolutely. Yes. So in 2D, this equation looks like this, and you have boundary conditions everywhere. And essentially, your Laplacian is going to have two derivatives, one in the x direction, two second derivatives, one in the x direction, one in the y direction. But then note the indexing. In the at any point ij, the second derivative in the x direction, you are relating points in the x direction. I plus 1, you fix j, okay, and you do I plus 1, I minus 1, and I. For the y derivative, you fix I, and you relate points in the j direction. Okay? It's just going to increase your number of unknowns in your coefficient matrix and the vector, but it's the same procedure. Okay? You just apply it at every point. If you are in doubt, put a grid, write a grid, and just do the discretization at 1 or 2 points. Okay? If you are in doubt. Actually, you should always do that to the point where it becomes second nature. Okay? All right. So now we go back to the time derivative. We haven't discussed the time derivative yet. Time is interesting because it's not space. And so time has a uniqueness because it kind of has one arrow. Okay? In space, you can go back and forth, but time, you can never go back. There's only one direction for time. Okay? So the presence of time in all of these governing equations, although we will use the same approximation for the time derivative, it just looks like a derivative, but the meaning is very different. Okay? So I'm going to present to you some new animations I was working on over the weekend. Hopefully they'll explain how we do the time integration a little bit more interestingly. Okay? So just like we did with the finite difference, we're going to do the same thing for the time derivative. But you have to pay attention that you have to recognize that this time derivative, we're going to apply it to every point in space, right? So when we did, yes. So when we did du by dt equal right-hand side at I, so at every point in space, we have to advance that point in time, okay? So I'm going to take a snapshot, a piece of the grid, okay, around point ui, and I'm going to only show ui minus 1 and ui plus 1. But this grid extends all the way to u1 and all the way to um, okay? We're going to call the last point now m, because I'm going to use n as a different index. The spacing is delta x between these points. Now, when you have time and space combined in a partial differential equation, you require an initial condition and boundary conditions. Okay? So I'm going to start with my initial condition. I'm going to take this 1D problem, this 1D grid. This is a snapshot of it. And I'm going to assign this initial condition an index n equals 0, time t equal t0 or 0, and for all practical purposes. And I'm going to add a superscript, an additional index for my variables that is going to correspond to the time level. So ui0 is going to tell me that this is the initial condition or the value of ui at time t equals 0. Same thing for ui minus 1, same thing for ui plus 1. Okay? Clear? Okay. So typically, this is given to you. You start with this. Okay? You start with this initial condition. Okay? Now, the goal of the time integrator or the time derivative, if you look at the time derivative, what does the time derivative do? What does it do? It's going to take all of these values, and according to a recipe, okay, it's going to move those values forward in time. So discretely, obviously, this exact derivative partial by partial t, we can't do it exactly. So we have to use the same concept we used for the spatial grid where we had a delta x. We're going to move now all points in time a distance delta t, so that our new time level t1 is the previous time level plus delta t. Okay? And we're going to assign that time level n equal 1, so that our solution variables now, we started with ui0, now we're going to call it ui1. Now, how we went from here to there, okay, that's the recipe of the time integrator. Okay? That's the recipe. What is the relation between ui1 and ui minus ui0? That is going to be part of the time integrator recipe. Okay? So now we do the same thing. We can compute, let's say somehow we can compute this state at n equal 1. We do the same thing. We move it to n equal 2, etc., all the way to n minus 1. So we took between here and there n minus 2, or between here and there we took n minus 1 steps. Okay? So in other words, tn minus 1 is t0 plus n minus 1 delta t. Okay? In practice, when we implement this, you have a loop So you know the previous time, you just add the delta t to it. So that's why I'm writing it in this form. Okay? And same thing, we use the same nomenclature. ui minus 1 at n minus 1, ui at n minus 1, ui plus 1 at n minus 1. And you repeat the same procedure all the way, to the end time, okay, whatever you specify. But I needed to continue this the same way we did ui plus 1, ui minus 1. I'm going to use un plus 1, and un minus 1 to do time derivatives. Okay? Okay, give me a second now. Okay, so now there are two types of time integrators. Let me go back, sorry. Gave away the solution before. Okay. Okay, so that's great. Now we have the spatial grid going in this direction, and the temporal grid, right? This is a grid in time. If you think about time as another dimension, this is the time dimension. If you had a 2D problem, this guy would be a 2-dimensional grid that is repeated over time. Okay? If you had a 3-dimensional problem in space, you'd have a cube here maybe, and then that's kind of repeated over time. Okay, but it's just easier to illustrate in this direction and see the perspective. We're trying to go in time. So fix this image in your mind. It's going to help you think about time integrators. Okay, so in general, though, there are two types of time integrators, and those are explicit and implicit time integrators. So who remembers what an explicit time integrator is? What is, yes? Okay, so let me explain it in my naive understanding. Explicit time integrators use known data to predict the future. So our goal with these time integrators is to move the grid, the spatial grid, from one time level to another. Okay? Explicit integrators use known time levels, use everything we know, and essentially make a prediction of the future. So, in other words, if you are at point n and you're trying to predict n plus 1, an explicit time integrator is going to use all previous points. It's going to tell you un plus 1 is related to everything at un, even un minus 1 or un minus 2. That's a property of the time integrator. But it only depends on, it could depend on the past this way, or that way, whatever. But it only depends on the past. It doesn't depend on the future. Okay? So, for example, the forward Euler method is an example of an explicit method where you take your time derivative, you evaluate it at time level n. So now we got rid of the question mark here. And the forward Euler method says un plus 1 minus un over delta t. So that's just a derivative, right? Un plus 1 minus un over delta t equal. Now your right-hand side is going to tell you whether you're using the past or the future. So if we evaluate the right-hand side at time level n, then that's all known information. Do you agree? Yeah, it's obvious. So what does that mean? That means for explicit integrators, if you solve for un plus 1, you're going to get an algebraic relation at every point in space that just tells you un plus 1 equal something about un. And then you move to the next point, and to the next point, and to the next point. You don't use anything from the future. It's just simple algebraic update at each and every point in space. Okay? Be very attentive to the time level we are using here. This equation needs to be evaluated at the same time level and the same point in space. Okay? Remember, this has derivatives in it, but they're all going to be evaluated at n in this case. Okay. Now, what about implicit time integrators? Can you explain it in my intuitive words? Yeah, you use the future and the past to evaluate the future. How can this be? Well, just kind of to illustrate this for you. So let's say an example of an implicit method is the backward Euler method. It says, okay, I'm going to evaluate the derivative in time at n plus 1, and I'm going to use a backward method. So that gives you un plus 1 minus un over delta t, but the right-hand side is evaluated at n plus 1, okay, at this time level. So then, essentially, pictorially, what happens, un plus 1 is coupled to all the other points at time level n plus 1, and could be coupled to other points at time level n. But it's this coupling in the future that make implicit methods a little bit harder to solve. Why? Because now you cannot just say un plus 1 equal something that's known. You don't know Rn plus 1. You don't know the right-hand side at n plus 1. So in general, if the right-hand side is a nonlinear function, let's say you had sine u, you're going to have un plus 1 equal sine un plus 1. That's a nonlinear equation. So you would need a nonlinear solver to solve for implicit methods. So an implicit integrator, in general, is going to lead to a nonlinear system of equations. And I write it here in kind of general form. Uin plus 1 minus delta t, right-hand side, function of things at n plus 1, at n, whatever, but it has n plus 1 in it. So that makes it a nonlinear equation. And at every point, you're going to have a nonlinear equation that's coupled to other points. So you're going to end up with a system of nonlinear equations. Computationally, that is expensive and annoying to implement. But it has a lot of advantages. Okay, it has a lot of advantages. And we'll see in a couple of examples. So now I want you to get your laptops out. We're going to do a couple of examples. Okay. Let's see if we have time. Okay. Okay, so I want you to point, if you have a local installation of Python or Jupyter Notebook, feel free to follow through that. But if you don't, just get your laptop and go to the following address, ched6355.chpc.utah.edu. So that is our own Jupyter Python programming environment that you can use in a web browser, okay, for dedicated specifically for this class. Okay, so you can use it. It has a lot of resources. Feel free to use it. You go there, okay, enter. Just type in your university unit and password. Okay? Were you able to get in? You have a local? Do you have a local? Okay. Okay. Okay, looks like you all have a bunch of local installations. Since you do that, you have that. I'm going to use my own local installation. Okay. I'm going to create and go to CHEN, Spring Lectures, Finite Difference Method. We're going to use a new. Okay. So now the first problem we're going to solve, if I can get my mouse. Okay. So now we talked about explicit and implicit. And this is just a warm-up. Next week, next Thursday, we will do a more thorough analysis on the advection diffusion equation. But the first example I'm going to give you is a simple advection equation given by, let me correct this. Okay. 1 second, please. So the first example we're going to do is a simple advection equation. Du by dt equals some constant c times du by dx with an initial condition given by u any point in x time t equals 0. That's u0 of x. So we're going to do like a Gaussian. And the advection equation, the purpose of advection is to move things. Okay, move things in space. Okay, and the first example we're going to do a forward Euler method for the time derivative and a central method, second order method for the spatial derivative, right? Because the second order method is higher order, so it makes more sense to do a second order method, right? Because it's going to give us a lower error. So what does that give us? The time derivative with the forward Euler, un plus 1 minus un over delta t. And the central derivative in space is ui plus 1 minus ui minus 1 over 2 delta x. Now, note the time levels. Okay, because this is an explicit integrator, everything on the right is evaluated at n. So we put an n over here, and this is un plus 1. So at any point I in our computational domain, this is our algebraic recipe, uin plus 1, so that's the prediction in the future, is uin plus c delta t over 2 delta x, ui plus 1 minus ui minus 1 at time level n. Now, pictorially, this is saying un plus 1 depends only on ui minus 1 n and ui plus 1 n, okay? And ui n. Yeah, there should be also an arrow over here, okay? Okay, so we're going to go ahead and implement this. I don't know your Python, how much Python you guys have done before. Who hasn't done any Python before? Okay, so you're familiar with NumPy arrays, and are you familiar with slicing in NumPy arrays and things like that? Okay, so we're gonna cover some of those. Okay, just okay. Okay. So now the first thing I'm gonna do is just import some boilerplate, and let's see. Import some boilerplate. I'm just gonna paste them. I'm importing NumPy as np. These two magic lines. So this guy is going to tell matplotlib to immediately plot in the Jupyter notebook, and this guy is going to tell matplotlib to produce scalable vector graphics. So these are really high quality graphics that you can see in your Jupyter notebook. Now, who hasn't used Jupyter notebooks before? Okay, so what's a Jupyter notebook? A Jupyter notebook is essentially an integrated development environment that in which you can combine text, math, graphics, HTML, and code. Jupyter notebooks are most popular with Python, but you can use them with C, with Fortran, with R, with whatever. So just to give you an example, for instance, let's say I'm going to turn this into a text cell. You've never done any Jupyter notebook before. You're okay. So you're familiar with some how to create a cell and okay. So we'll just start here. Then import matplotlib, and I'm gonna need an animation, the animation package to create an animation. Okay. So now let's say we start by defining the number of grid points. Start by defining L, the length of the domain. Let's say the length of the domain is 10, because I'm not gonna put in boundary conditions yet. I just want to put a initial condition in the middle of the domain and just have it move a little bit away from the boundary conditions, because we'll discuss boundary conditions later. Okay, so I'm just gonna kind of put it away from the boundary. So I'm gonna pick a very large domain, L equal 10, going from 0 to 10 essentially, and I'm gonna do 101 grid points. Then dx is simply L over n minus 1, correct? Okay. Now, this is good. Now, let's create the initial condition, u0. Let's say we want to do a Gaussian. So np dot exponential minus x minus, let's say, where are we going to put it? 2, okay, squared over standard deviation, let's say 0.05. Okay, and let's plot this. So to plot this, we need an x variable, okay, to designate the x locations. And you can do this with linspace, numpy dot linspace. Okay, going from 0 to L with n grid points. Okay, and then plt.plot x u0. Okay, x is not defined. Oh, of course, x is not defined because it needs to be before u0. Okay, so look at our pulse. It's pretty narrow because I have a small number of grid points, so we can do 300 grid points. Makes it, or just decrease the standard deviation a little bit. Okay, makes it just a little bit smoother. Maybe 0.1. Okay, does this look fine? So that's our initial condition, and the advection equation is going to tell us how to move it to the right. We want to move it to the right. Okay, yes. Sorry. Is this good? Is this good? Okay, maybe one level down. Okay. Okay. All right, so now let's simply implement our formula. Okay. Now, if you remember, let me just get the formula in here. Okay. So this is the formula we want to implement. We want to say u new is equal to u old plus c delta t over 2 delta x times u old I plus 1 minus u old I minus 1. Okay? And we'll show you how to do that pretty neatly. So first things first, I'm going to define a time step size. And I'm just going to arbitrarily pick like 1e to the minus 3. Okay? I'm going to define the end time as 1 second, the initial time as 0, the wave speed minus 1, so that's wave speed, so meters per second. So why the negative sign? If you want the wave to move to the right, c needs to be negative. If you want the wave to move to the left, or the signal to move to the left, c has to be positive. Okay? You can change that number. So now I'm going to put all of these guys, c delta t, 2 delta x, I'm going to put them into a number. I'm going to call that CFL. There's going to be c times dt over 2 delta x. Is this clear so far? Okay. Have you done this kind of analysis in your applied math class, or do you do just ODEs? Okay. Please stop me. Because I know most of the students here have done this before, so I'm going through this somewhat fast, but please do stop me if something doesn't make sense, okay? Same for you, Tim, okay? Okay, great, okay? Okay, so now I want to, because I want to visualize how this solution evolves in time and space, I'm going to create an empty list to store my solution in, and then animate that solution, okay? So I'm going to declare a solution as an empty list to which I can start adding solutions. Now, the first entry in my solution is going to be the initial condition. So how do I, this is empty now. This line declares a sol variable that is empty, an empty list. First thing I want to do is add the initial condition. So I do sol.append, so add at the end, u0. So now sol contains in its first entry an array u0. Okay? Now the fun begins. We want to integrate over time. So while my current time is less than the end time, or less than or equal to t end, do something. Okay? And in this loop, the first thing or the last thing I want to do is increment my time by delta t. Okay? So initially t is 0. And then every time we hit this while loop, we increment our time by delta t. Okay? So the first thing I need is the old value, correct? So I need un. There's un everywhere over here, so I need the un values. Okay? So first thing I call un is solution. Where am I going to get the old value from? We're going to get it from the solution list. Okay? So solution, if you think of solution, what is it going to contain? Sol is going to be a list that contains u0, u1, so t equals 0, t equal n, or n equals 0, n equal 1, u2, etc. Now each one of those is an array, u0 or u1, right? u2, etc. Okay? Okay. Now Python is great in the sense that arrays, if you should think of arrays as as entries in an array lie on a circle. Okay? So you can index on the circle, you can index positively in this way. So if this is entry 0, or the first entry, this is the first entry, this is the second entry, this is the third entry. If you index positively, you move in this direction. Okay? So and this would be the nth entry. Okay? If you index positively, you move in this direction. So if I say sol 0 is going to give me this guy. If I say sol 1 is going to give me this guy. Why 0, 1? Because Python is 0 based. Okay? But essentially what you have to remember is that sol 0 is the first entry, sol 1 is the second entry, and so on. But what if I do sol minus 1? It's going to give me, it's going to index in this direction, in the negative direction. So sol minus 1 is going to give me the last entry. Okay? Sol minus 2 is going to give me the second from last entry. Okay? So how do I get the most recent solution? So sol contains all of these guys. Right now, it only contains u0. Okay? And the next step is going to contain u0 and u1. How do I get the most recent solution? Sol minus 1. Yep. Exactly. Okay. So I have 5 minutes. Sol minus 1. Okay? Now I declare a new variable. Unew is un.copy. And I think you asked me about this last time, the difference between pointers in Python. Did you ask me about that? Yeah. So this is an example where I want to create my new solution. My new solution is going to look like the old solution in terms of how many points it has, right? Because we've taken the initial condition, we want to move it forward. So we have n points, okay? But rather than saying unew equal un, I need to make a copy of un. Because if I say unew equal un, any change to unew is going to change un, which is going to mess up my solution. So by making a copy, I make sure I copy the memory into a new location. I create a new space in memory. Okay? Now, since we're not going to deal with boundary conditions, I only want to apply this formula on the interior points. Okay? So Python, again, is great in terms of slicing through an array. So in other words, if I want to apply the solution only on the interior points, and I'm going to show you now above, on the top, I'm going to show you the human indexing. So this is 1, 2, 3, etc., and this is n. The Python indexing, Python, is going to be 0, 1, 2, all the way to n minus 1. Or also, in terms of circular indexing, 0, 1, but this guy is minus 1, minus 2, and so on. Okay? So now how do I apply my formula only on the interior points? I need to take a subset of the array. The array u is going to give you all of these points. But then, if I only want to go from 1 to this last one over here, all I have to do is say going from 1 to minus 1. Now, why minus 1? It's kind of quirk in Python. because this is an open domain, essentially. So 1 to minus 1 is going to give you only these points. No, because this is a slice. So that's the quirk in Python. Because u minus 1 is indeed going to give you this guy. But when you do u1 to minus 1, it's going to do an open bracket at the end. So like math intervals, a to b is always going to be an open bracket at the end. So it will go from this point to this one before last. But it includes closed bracket on the left and open bracket on the right. Yes. And if you're in doubt, do this. Say a equal 1, 2, okay, 1, 2, 3, 4, 5. A 1 to minus 1. Look at that. 2, 3, 4. Okay? But a minus 1 is 5. Okay? If you're in doubt, just test. I forget this sometimes. If I spend a month without doing this, I'm like, okay, what is this? Couple of tests. You remember what you're doing, and then you go back. As long as you kind of know what you're after. So you knew from 1 to minus 1. I know I'm out of time, but if you can spare a few minutes, we'll be done with this. Okay? Is equal to u old, also on the interior. So what is that formula? Okay. So same thing, ui at n plus 1, ui at n. So that those are the old points. Plus CFL times. Now, how do we do un plus 1, ui plus 1 minus ui minus 1? Okay. How do we do this? How do we do this using smart indexing in an array? So if you think about it, at every point I, we are using the point to the right and the point to the left. Now, the points to the right of point I, okay, they are a subset. Okay? So they, with respect to this point, you're going to need this guy. And with respect to that point, you're going to need that guy all the way to the end. So then ui plus 1 is really u going from, so all the way from 2 to the end. Correct? So that's the subset of points to the right of this guy, all of these points. And then ui minus 1 is simply u starting from the beginning all the way to minus 2, to this guy. So that gives you the points to the right and the points to the left of any point I. Okay, so let me give you an example. Okay, so again, we'll go with the array. This may be kind of the hardest piece. Okay, so if you do u, let's say 2 to the end, that's going to give you 3, 4, 5. So essentially, when you're dealing with point 2, you're using point 3. And then for point 3, you're going to be using point 4. That's ui plus 1. And then the other one is u minus 2. So that's going to give you the other set, u1, u2, and u3. Okay? I know it's too much, but I'm going to show it to you anyway. Okay. So now that we've updated u and u, we solve for u and u. We're going to append it to the solution variable. Okay? And that's it. Okay, so that's the solution now. Okay, so we can plot. So plt dot plot x. The initial condition is going to be sol 0, right? Then the first one is going to be sol 1, and then sol 2. It's barely moving, right? So sol 10. So it's still kind of barely moving, right? Let's see, sol 100. Well, it's not moving. Delta t sol. must have a typo in here. Okay. Okay, so it is moving. It is actually moving, right? So let me do some magic animation here. So I'm just going to get this stuff out of here. Okay. GCS. And then I'll show you how to do the... Okay, so this should actually crash, but it's not crashing. Murphy's Law, huh? Okay. Okay. First step, let's see. Okay. So it is actually moving very, very slowly. Okay, so that's the animation.